Hey Trig class, this is section 3.4a, which is the excursion section. It's kind of like part B of section 3.4. 3.4 we did all those transformations like the up, down, left, right, stretches and compressions and all that good stuff, okay? So 3.4a is going to focus on symmetry. We do this again at the end of Trig class, and then we will talk about this a lot in calc class as well. But there's three types of symmetry that we need to look for. And the first one is y-axis symmetry. The second one is x-axis symmetry. And then the third one is origin symmetry. Okay, so we're going to talk about each one of those three. Y-axis symmetry just means that it's symmetric with respect to the y-axis. So if I'm looking at the graph of a function, it has to be the same on either side of the y-axis. So like a parabola would do this because he's the same on both the right side and the left side. If I would take him and fold him over top of the y-axis, it would like land on top of itself, okay? And the way that I think about y-axis symmetry is in art class, maybe in like elementary school. Do you guys remember doing like you'd take a sheet of paper and then you'd fold it in half and then you'd paint something on the one side and then you'd fold this over. And then when you unfolded it, it looked the same on both sides of the sheet of paper. That's kind of what y-axis symmetry does. It's taking that paper in the middle right here, the fold, that's kind of like the y-axis. And you fold it in half and then it's the same on both sides. So this circle right here, or it's kind of an oval, I guess. It's the same on both sides of the y-axis. So what's over here is also on this side. So he's literally folded in half. Their y-coordinates are the same. Their x-coordinates are opposite of each other. The y-axis is perpendicular bisector of PQ. Don't get too bogged down with this information here. But just know that it just kind of folds on top of itself. It is symmetric, okay? Now, the y-axis is the axis of symmetry. You might hear that term used. The axis of symmetry is just kind of like where the fold is located. So that's kind of how that works, all right? Now, how you test for y-axis symmetry. If I'm looking at the graph, it's very easy to see that he is symmetric with respect to the y-axis. But if I'm looking at an equation right here, I don't want to have to graph that thing in order to figure out if he is symmetric. So what I do is called an analytical test, which sounds like a really big word, but it's not a very hard procedure. What I do is points that have a y-axis symmetry. Okay, let's talk about this for just a second. If I'm looking at this point right here, which is the point, I'm going to make this up, 2, 3, and I want to make him symmetric with respect to the y-axis or reflect him across the y-axis, he's going to be this point over here, which is the point -2, 3. So when I flipped him over the y-axis, he became negative for the x-coordinate, okay? So what I do is to test this function right here to see if he has y-axis symmetry is I take all of the x's and I make them negative. I leave the y alone because this 3 stayed the same, right? But the x's, I make them all negative, okay? So we're going to go through and we're going to do that, and I'm going to tell you how you can tell whether it's whether it's symmetric or not. So all of these x's I'm going to take and I'm going to plug a negative x in there, and this is what it's going to look like, okay? Negative x to the 4th, I'm just taking this x and I'm plugging a negative in there, -5 times negative x squared plus 3. Okay, I'm just taking all these x's and I'm plopping a negative in there. Okay, and so what happens is if I take negative x to the 4th power, if I simplify this, negative x to the 4th power means negative x times negative x times negative x times negative x 4 times, right? So I have a negative and a negative and a negative and a negative, which is going to turn that to positive. So really negative x to the 4th power is kind of the same thing as saying positive x to the 4th power, okay? Because the negative, there's 4 negatives, which is going to make a positive. -5, and this negative x squared is going to kind of do the same thing. Negative x squared means negative x times negative x, which is going to end up being positive. So that is positive x squared. If I'm going too fast, pause the video or rewind. You can always do that. Positive x squared plus 3, okay? So when all is said and done and when everything is simplified, what comes out is a function looking like this. If I simplify all my negatives, he looks like that, okay? And then what I do is to see if that is symmetric. Oh, I erased more than I needed to. To see whether that's symmetric or not is I look at the original equation. This was my original, and this is what it came out to be when when I simplified all my negatives. And what you'll notice is both of those things are the same function. So when I plug the negative x in, he turns back to normal. So when that happens, he is symmetric with respect to the y-axis. So yes, y-axis symmetry. And the reason why he did that again is because when I simplified the x's, the function that I ended up with was the same as the function that I started with. Okay, so the same thing happens with x-axis symmetry. So this guy has x-axis symmetry. He is a parabola that's kind of on its side. So it's kind of like my axis of symmetry is the x-axis. He's folded. If I fold him down, he will lie on top of himself, okay? And when I'm doing x-axis symmetry, let's say I take that point that we talked about above, which is the point 2, 3, and I reflect him across the x-axis, because that's this guy. If I reflect him across the x-axis, he will be the point 2, -3. So what's happening there is, when I reflect him across the x-axis, the y-coordinate became negative. So I'm going to do the same thing, x negative y. I'm going to plug in. So all of the x's are going to stay the same, but the y is going to become negative. So I'm going to do that real quick. And every y that I see, I'm going to plug negative y in. But all the x's get to stay as the regular x, okay? Because this 2 right here didn't change. Only the 3 changed. Only the y-coordinate changed. So I plug a negative in for the y, okay? And you guys can probably already, some of you, maybe identify what's going to happen here, because negative y squared, kind of like above, negative y squared was negative y times negative y. And negative y times negative y is going to be a positive y squared. So really, this guy simplifies to be y squared. And then the rest of it just stayed the same because we didn't change the x. So this is what it simplifies to be when everything is said and done, which, is exactly the same as the original function. So what that tells me is he is, yes, symmetric with respect to the x-axis. He does have x-axis symmetry. Ooh, I did not spell that right. I can't spell while I talk at the same time. X-axis symmetry. There he is. Okay, yes, he does have x-axis symmetry, so that is fabulous. All right, origin symmetry. The origin is the point 0, 0. So let's talk about that point that we keep referring to, the point 2, 3. Okay, origin symmetry is kind of like saying both x and y axis symmetry. So it's kind of like taking that point and reflecting him across the x-axis and then reflecting that point across the y-axis. And what that's going to do is that's going to land me a point over here. It's kind of like reflecting him through the origin, through this origin point. I'm going through there, okay? And that point is going to be the point -2, -3. So what you'll notice is from the one side, from the point 2, 3, to this new point across the origin, both the x and the y became negative. That's kind of what the rule says right here, negative x and negative y. So what I'm going to do is to check for origin symmetry I'm going to make all of the x's and all of the y's become negative. So every x that I see is going to become negative x. Every y that I see is going to become negative y. So what we're going to test in example 3, which is on the next page, is he symmetric with respect to the origin? Okay, verify that he is symmetric with respect to the origin. So all of the y's I'm going to replace with negative y. All of the x's I'm going to replace with negative x minus negative x. So I put that in parentheses, and then we're going to simplify, okay? So I really just want to, what I want to accomplish is trying to get rid of the parentheses. So negative y in parentheses, those parentheses aren't really doing anything, so I'm just going to write him as negative y. And then negative x to the third power. That means negative x times negative x times negative x 3 times. Will that stay a positive, or will that stay a negative, or will that turn to be a positive? Up here, when we did like y to the 4th power or x to the 2nd power or an odd or an even power, he became a positive. But I have 3 negatives here, negative, 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 so that's going to stay as a negative x to the 3rd power. Okay, all over 10. And then negative and negative became a positive x. Okay, so this is what I have right now. This negative, if you want to, you can bring him out in front. So I have negative x to the 3rd power over 10. And then what I do is I look at that thing and I say, okay, is this the same thing as what I had to start with? Well, not really, because the y is now negative, and this x to the 3rd over 10 is now negative, and this negative x is now positive. So that's not the same thing. So it's not symmetric with respect to the origin, except I'm going to rewrite this guy. Negative y equals negative x to the third over 10. I'll just make this a little less messy, plus x. What I can do is these three pieces right here, these three pieces, if I divide by a negative 1 on everything, that will flip this y back to just y. This negative x to the third over 10, if I divide that by negative 1, that will switch it back to positive x to the third over 10. And this x over negative 1 will become negative x. That's what he will look like. And because I divided by negative 1 to all of the pieces, it is legal. Is that the same as the original? Yes, you betcha. So he is symmetric with respect to the origin. Yes, origin symmetry. T-R-Y. He does have origin symmetry, so that's awesome. So sometimes it's kind of tricky when you do origin symmetry, because if it flips everything to be the negative of what the original was, you can just divide by a negative and it will turn it back to positive, okay? So that's one little trick with origin symmetry that doesn't usually occur with the other two, okay? So symmetry tests, when you're doing y-axis symmetry, this is just kind of a summary. When you're doing y-axis symmetry, you plug the negative in for the x and the y stays the same. For x-axis symmetry, you plug negative y in and leave the x the same. Origin symmetry, you plug a negative in for both. And you look to see if it becomes the original function, okay? So the last thing down here is even functions and odd functions, okay? So an even function, it is considered to be an even function if it has y-axis symmetry. That's it. They just call it even. So if it's said to have y-axis symmetry, it's considered to be an even function. So one of the functions that I set up above that had y-axis symmetry, I set a parabola. A parabola is y equals x squared, and the way that I can remember that is even functions. This guy is squared. Okay, even, it has a power that is even. Okay, odd functions have not y or x-axis symmetry, but origin symmetry. Origin symmetry. So if it is symmetric with respect to the origin, it is considered to be an odd function. Now, that's it. It's either even or odd, or it could be neither even or odd. So some functions, like even if it's a parabola, it's not necessarily an even function, because this doesn't have y-axis symmetry if he's moved over here to the right. So that is a neither function. So it doesn't have to be even or odd. It could be neither function. But what is it called if it has x-axis symmetry? Okay, like it's not even or odd or whatever, it's, what is it? Well, if it has x-axis symmetry, like let's say this guy right here, the reason why there's not a special name for x-axis symmetry, like even or odd, is because something that has x-axis symmetry is not even a function. If you do the vertical line test, he doesn't pass, right? So that's why x-axis symmetry doesn't have a special name for him. Only y-axis symmetry is even. Origin symmetry is odd. You could have functions, and in fact, there's a ton of functions that are neither even nor odd. So let's talk about these up above here. Which functions from the above examples are even and which are odd? Okay, so example 1, we said did have y-axis symmetry. He was a yes y-axis symmetry. So this is considered to be an even function. The function y equals x to the fourth minus 5x squared plus 3, that is an even function, okay? This one had x-axis symmetry. So y squared equals 4x minus 12. Is he even or odd? No, y-axis symmetry is bad. Well, not really bad, but it's not a function. So this is a neither even nor odd. It is symmetric with respect to the x-axis, but that's not really anything special. It is neither even nor odd. That's example 2. Example 3, did yes have origin symmetry? So this function right here, y equals x to the third over 10 minus x. This was an odd function because he is symmetric with respect to the origin. Okay, so even odd means y-axis, origin, the x-axis symmetry is neither. Okay, now, if he does not have any of those symmetries, because he maybe doesn't even have y-axis, x-axis, or origin symmetry, then he's also neither. Okay, so if it has x-axis symmetry or it doesn't have any of those symmetries, it's going to be a neither function. Okay, so hopefully that made enough sense. We talk about that a lot, again, at the end of trig class, like in the spring, and then we'll talk about this in calculus as well. Okay.